Our next speaker is Professor Marco Tomamichel. Could you switch? Okay. So he will speak to us about communication in the age of noisy intermediate scale quantum computers. Before that, let me briefly introduce Dr. Marco Tomamichel. So he is an associate professor at the Department of Electrical Engineering and Computer Science at the National University of Singapore, and a principal investigator at the Center for Quantum Technologies in Singapore. His research interest lies in the intersection of cryptography, information theory, and quantum mechanics. Marco Tomamichel received his master degree in electrical engineering and information technology from ETH Zurich in 2007, and his PhD in physics also in ETH in 2012. He then did his postdoc at CQT in Singapore. He also has been a research fellow at the University of Sydney and an associate professor at the University of Technology, where we have been a colleague in the past. Dr. Tomamichel is an associate editor for IEEE Transactional Information Theory and on the editorial board of Proceedings of Royal Society 8. So let's welcome Marcos. The floor is yours.
Thank you very much. Thanks a lot for the invitation and the kind introduction. So today I'm going to talk about communication in the age of noisy intermediate scale quantum computers. And I'm going to tell you a little bit what I mean by this and maybe mention some, I think, interesting open problems. It also says cryptography on the slide, but I don't know if I will actually get to that. So maybe as a motivation a little bit, we're all talking about the quantum internet nowadays. So there have been many proposals on building test nets. Some of them are visions, like the one you see on Europe is not built, but in mainland China the network is actually standing, yeah, also in Singapore we're building one. So what are the actual challenges between what we have now and such a quantum internet, a real working quantum internet? So I see the challenges kind of in two categories. I would say mostly the challenges are experimental. So we don't actually have a good way of producing entanglement that is reliable on demand. Usually we get a heralded entanglement, so we are told when the entanglement is created, but we can't really decide on what time that happens, and that creates a lot of problem with scalability of such if you try to connect different nodes in a network. Again, quantum repeaters, that's an often heard topic that we need to develop. And most importantly, also interfaces between photonic qubits that we can send through a network and stationary qubits, like in a solid state device that we can store and compute on. So these challenges are immense, and I think there's steady progress, but we're still quite far from where we want to be. Now, for me as a theorist, the challenges are a little bit different. The challenges have to do with the question, if we had a quantum internet, what would we actually do with it? So that's the first challenge. So we need to find more applications for a quantum internet that go beyond just quantum key distribution. Quantum key distribution is a kind of an application that has been developed, even commercialized, and has some interest for specialized problems, but it's not a big seller. So we need applications that are actually really solving problems that we can't do with classical networks. So yeah, this, I think, as theorists, should be our main focus. Then the other focus as here is finding protocols for communication and networking with limited resources. And so that's going to be the topic mostly of this talk. Okay, so what I want to talk to you about is kind of it's a relatively early result in this direction, and it's a basis of many works that have been done afterwards. So and it has to do with classical quantum channel coding. So the way I want you to think about this is that if you send information through a channel, and here it's a classical channel, then this is the usual problem of encoding a message into channel inputs and then decoding it again at the output. Now, you can think of each classical channel as having a physical implementation, right? And physics is governed by the laws of quantum mechanics. So I can kind of decompose a channel, and this is the image at the bottom. I'm just decomposing it into first a preparation of a quantum system, then a quantum channel acting on this quantum system, and at the end a detection of that quantum signal, which then again returns it into a classical signal. Okay, and so obviously if we do this, we might also ask, well, if we now look at these underlying physical quantum channels, can we maybe transmit more information over this system? And the simplest kind of model for this is to make an assumption, maybe an assumption that the state we prepare at the input is a product state, or at least a separable state. And this leads to this classical quantum channel coding. So we don't have a quantum computer at the encoder. We just prepare quantum states in a product form, maybe with some randomness. But on the decoder here, the assumption is that we do have a quantum computer. So we actually collect all the quantum signals and do a joint operation on them to figure out the message, this M hat. Okay, so this requires, I mean, this is technologically very difficult, because we need to collect all these signals that we get from the quantum channel and then do joint operations on them before we do the measurement. So very difficult to implement, and the question then is, well, what can we do with this? This was solved by Holevo, Schumacher, Westmoreland. They showed us the capacity of such a channel, so that the rate at which we can send information in bits per channel use converges as n goes to infinity to the Holevo capacity, and at the same time the error can be made to go to 0. But as I said, this decoder is very difficult to implement, so the limit n to infinity might not be a good way of looking at this, because it means the decoder has to look at a very large number of qubits at the same time. And in the NISQ area that we are in at the moment, this seems out of reach. So instead, many people developed kind of a theory that allows us to deal with finite block lengths. So for classical channels, this has been done by Polyansky, Poor, and Verdu in kind of a seminal paper in 2010. And for classical quantum channels, we can do a very similar thing, or essentially the same thing. We define for a fixed number n the maximum number of different messages that we can send through with an error that is less or equal to epsilon. So that is just the definition of an achievable triple. So with the number of messages m, the block length n, and the error epsilon. And then we can look at this quantity, which is the maximal number of messages that we can send for a fixed n and epsilon. And essentially, we want to understand how this quantity behaves asymptotically as n goes to infinity. So the simplest way to do this is to kind of recover the whole level capacity that we had before. So if you look at 1 over n times log m star, which is exactly the number of bits we send per channel use, and look at the limit, the large n limit, we see that this converges to the whole level capacity. And in fact, we see a behavior that is also called the strong converse of channel coding, which tells us that if we try to transmit at a rate above the capacity, above the whole level capacity here, then the error will go to 1. Whereas if we are below it, then we can make the error go to 0. Also, there's this step transition. But as we decrease n and don't look at the limit n to infinity anymore, we see that this transition actually becomes smooth. And this is called the second order approximation of this transition. And we see that, for example, if you have 40, n equals 40, then and you want a certain error, then the rate has to be much below the capacity for this to be possible. Okay, so you lose something due to finite size effects. Now, formally, we can write this down as an expansion. So we're just expanding this quantity, well, the log of this maximal number of messages, and divide by 1 over n. So if we do this, then the first term we get is exactly this whole level capacity. And then we get the second order correction that scales with 1 over square root of n, and also has a dependence on the error now. And so one of the interesting things about this is it's kind of similar to what we get classically. Well, in fact, it's the same type of expression we get for classical channels, except that we have the whole level capacity, which can be larger than the classical the capacity for the classical channel, where we kind of forced to do a measurement on each output separately. But also these kind of terms, if you're mathematically inclined, they have a nice geometrical interpretation. So we can think of the whole level capacity as a divergence radius of the channel. So we just look at, essentially this measures how far away different outputs of the channel are for different inputs. Like if you can spread them very far, then you get a larger radius and you can transmit more information. And then we can define the channel dispersion kind of as the channel or the information variance, but just computed on some decomposition of this minimizer of the that gives the center of this channel image. Okay, so that's just a geometrical way of seeing these quantities. Now, just so for those who are a bit more experts on this, the main proof ingredients are essentially that we relate this channel capacity or channel coding problem to hypothesis testing. So we can define something here which is very similar to the information radius that we defined before, but now for some quantity that appears in binary hypothesis testing, yeah, which is this quantity here. So it's the minimal error of the second kind when the error of the first kind is bounded by epsilon. And then kind of the main result, the main ingredient of the proof is to show an expansion for this quantity itself. So to show how this quantity behaves when we have rho tensor n and sigma tensor n in here. That is kind of the main ingredient that allows us to give this second order expansion for channel coding. Good. So there were various results that followed after this. We looked at different channel models, quantum communication, private communication, and also different parameter regimes like moderate deviation. But I'm not going to go into these. I just want to end this part with an open question that I think might be interesting, maybe for some in the audience. So what we've looked at is kind of a scheme where the decoder has to be a fully fledged quantum computer, right? It has to deal with n qubits. And then the scaling of that is very difficult. So even to go beyond n equals 2 seems challenging at the moment, because we don't have, for n equals 2, we can still do everything optically, or maybe n equals 3 and so on. We can still do the decoding optically, but there are some gates that we cannot even reliably on optically. So even then it's very difficult, and we don't have a way to interface the optical signals with the quantum computer, even though in this picture it looks like we could do this, but we don't actually have a reliable way to do that. So we can't even use the quantum computers that exist for such a decoding task. Okay, so increasing n is very difficult. So what could we do? Well, one thing we can do is that we can use all the tools we have from classical coding, because classically it's not a big problem to deal with larger block lengths, right? So a natural kind of setup would be to have an outer code that just deals with classical information, and then use an inner code that uses the quantum nature of the channel to kind of create like a channel, a super channel that is classical, and that can then be used using classical coding techniques. So essentially, the outer encoder will give an input to this inner system, which will then use the quantum channels to transmit, and maybe even use with n equals 2 or 3, try to decode this and create some output. And this input-output behavior of the inner part will just be considered a classical channel, and the outer code will code on that classical channel. But the question I have here, and I don't have the answer for this, I don't think it has been analyzed, is how does the capacity of the system actually change as we increase n? Right? Can we find a quantum advantage that is somehow interesting, even for n equals 2, 3, and so on, for small n's? And how difficult would it be to actually implement this? So maybe there's a way to boost the classical capacity using such a hybrid scheme in a way that's already possible nowadays. Okay, so that's kind of the open question. Now I see I have 5 minutes left, so let me just give you maybe a very short introduction to this. So another topic, as I mentioned, is finding applications of the quantum internet. And so one thing we looked at is homomorphic encryption. And this is some recent research with my students. Homomorphic encryption is kind of a cryptographic primitive that's very useful in classical cryptography, because it allows to essentially instantiate all kinds of other classical protocols as special cases of it. So you can think of it as a Swiss Army knife of classical cryptography. And the question is, what can we do quantumly? So quantum homomorphic encryption here is the simple protocol where relatively simple, where Alice encodes using a key that only she knows, a quantum state. And then the idea is that Bob does some function on that state, or some map on that state, some channel, but without actually decoding the information. So the idea is that he won't know what state he's acting on, but we'll still do this evaluation and send kind of the encrypted state back, and Alice can then decode it and find out what the actual answer is. So what the function applied to her input state is. And the idea is that Bob should not learn what Alice's input was, and Alice should not learn what Bob's circuit was. So you kind of want to be secure against, the server wants to be secure against the client learning the implementation of the algorithm, right? Because maybe the implementation is actually proprietary. Okay, so we can define this, if we define it properly, we can then ask the question, can we have both data privacy, which is the privacy for Alice's data that she sends, and circuit privacy, which is the privacy for Bob's circuit, at the same time? And it turns out we cannot do this even for very simple schemes. So if we are interested in information theoretically secure quantum homomorphic encryption schemes, and really very simple ones, such that the only thing they can do is 2-qubit Clifford gates. So Bob can only do 2-qubit Clifford gates. But even in this simple case, it turns out there is a fundamental trade-off between the different parameters. So, for example, if we require perfect correctness of the protocol, then the sum of the data privacy and circuit privacy parameter must be larger or equal to 1/2. So it's an impossibility result for this. Well, impossibility results are as interesting as possibility results, maybe, because it tells us that there's a direction that we don't need to look any further in. But we're still interested to look at maybe if such quantum homomorphic encryption is possible in some specific model, like bounded or noisy storage models. Okay, and proof idea I will skip because I've been told to stick exactly to the time. So I'll skip that, but it's essentially a reduction to oblivious transfer. And with that, I want to thank you for your attention. And here I just have mentioned my group and some of my main collaborators that are this work has been done with, that I talked about. So thanks a lot for your attention.
Okay, thank you for the nice talk. Do we have any questions from online or from the audience? Okay, so we have one question here.
Hi, I was just wondering, like the homomorphic encryption, is this like this is I mean, you're using like a quantum circuit to do the algorithm to do the to encrypt, or I mean, it's different from QKD, right?
Yes, it's not related to QKD, so that. But
it's also not a post-quantum cryptography.
Well, there are classical algorithms that do homomorphic encryption, and they're based on post-quantum cryptography, on lattice-based protocols. But here, really, we actually ask for quantum homomorphic encryption. So the data that we operate on is a quantum state, and so it's a quantum state that is encoded, and Bob will act on the encoded state.
So I can consider this as like quantum version of post-quantum cryptography, and I can use this on the quantum computer?
A quantum version of homomorphic encryption.
Okay.
Yeah, post-quantum cryptography is the name used for classical cryptography that is
yeah.
secure against quantum attacks. So this here is also secure against quantum attacks. I mean, we require security against quantum attacks, but then we have an impossibility result, right? So we actually show that it's not possible to be secure against quantum attacks for such a scheme. Right? We show that it's not possible to have all of these security parameters small at the same time. You see it? Okay. Ideally, we would want both of these errors to be small, but actually this inequality shows that they need to sum up to more than 1/2.
Thank you.
So just out of curiosity, is this result on arXiv yet?
Yes, it's on arXiv.
Okay, then I will take a look. Any questions? Okay, I think we don't have any questions from either online or from the audience. So in that regard, thanks Marco again. Thank you for the nice talk.
Yeah, thank you. Thank you.
Yeah, hope to see you soon.
Yeah.